Okay. Hello, everybody, and welcome back to another neural networks from scratch video. Let me just give me a second to pull the stream up on my phone so that I could see questions and stuff like that. That would be ideal. Okay, great. All right, let's review a little bit about what we're doing here. This is the 10th part of the Neural Networks from Scratch series in Golang. We are going through the book, Neural Networks from Scratch in Python, but as you can see, the book is in Python. You can't see it. Okay, here we go. The book is in Python, and I am turning it all into Golang. A link to the book will be in the description, as well as you could just go to Google, type in nnfs.io, and that'll take you to their site where you could buy a copy of their book, either as an ebook or paperback or hardcover. Excellent book. Highly recommend it. They're not sponsoring me or anything like that, but I do have their permission to use their book, and yeah, I just recommend getting it because it's an excellent book if you want to get into machine learning and understand what's going on, and if you enjoy coding in Python, which I most certainly do. In the last video, we talked a little bit about the softmax activation function, which is the output activation function for our neural network. And just to see what we have going here, we have our main.py where we have a dense layer that we've made. We have an activation 1, which is a ReLU activation. We have another dense layer, and then we have an activation 2, which will be a softmax activation. And the softmax activation basically gives out just some review, it gives out a probability confidence. So if you're trying to do classification, and you basically put in an image, let's say, and the image is either a dog or a cat. So the softmax activation will take the outputs from the last layer, which will be 2 numbers probably, and it will basically put them in terms of percentages. So the algorithm is 30% confident that it's a dog, and 70% confident that it's a cat. And that's the softmax activation function. It's excellent for classification. The reason why we are using the softmax activation function is because our example here is a classification problem. We have these 3 classes, and all of them form this big spiral. And we're going to give the algorithm a point on this graph, and it will have to tell us what class it thinks it's in. So it will give us 3 outputs for the 3 classes, essentially. As well, we also have this data thing here, the data.go file. It has a bunch of x's, which are basically inputs. This is where exactly on the graph the given point is, and these are the inputs. And here we have what the expected outputs should be. So basically, the first location, the first x and y coordinate, should correspond to the 0th class, and then all these y's correspond to the given classes. So as you can see, it's all ordered, and we're going to have to randomize that at some point. Okay, excellent. Moving forward, we're going to start talking about loss and how to calculate loss. So this is the beginning of chapter 5, calculating network error with loss. And basically what loss is we're trying to determine how wrong is our model. So you can imagine we're going to give it like 5 inputs, 5 locations, and we know what the outputs should be because we have that data. We have the y. We have this y information as opposed to the x information. So we're going to look at what it gives us, and we're going to basically calculate, okay, how wrong are you? And that will tell us how we should tweak it and what we should tweak. So now we're going to start talking about calculating how wrong it is. Because we are getting the outputs. In the end, this is kind of like we're getting the outputs already. We have the activation 2.output, and if we run this, and this is using all of the x's actually. So this is the real data. Where can I run this, please? Terminal, new terminal, thank you. Go run everything. We coded all this in previous videos. Link to those videos will be in the description. So here are the outputs. Right now it's just each one of the inputs is getting a 3 because it's randomized, and so randomly it's like, well, I think this one is just as likely as this one, which is just as likely as this one. So I don't really know anything. That's what the model is telling us. So we're going to find out how wrong it is by looking at what it should have outputted and how far off its guess is from that output. Okay, let's check it out. With a randomly initialized model, or even a model initialized with some sophisticated approaches, our goal is to train or teach a model over time. To train a model, we tweak the weights and biases to improve the model's accuracy and confidence. To do this, we calculate how much error the model has. The loss function, also referred to as the cost function, is the algorithm that quantifies how wrong a model is. Loss is the measure of this metric. So loss, the word loss is like how wrong it is. Since loss is the model's error, we ideally want it to be 0. So we're looking to minimize the loss. We want loss to be as small as possible. The higher the loss, the worse we are. You may wonder why we do not calculate error of a model based on the argmax accuracy. So let's give an example. Imagine for example, the model outputted this when it should have outputted a 1, 0, and 0. In other words, saying it's 100% sure that this is the right class. Well, we could say that the model is wrong because it's the highest value is this. If you know what argmax is, it's basically what is the index of the highest value. And so the model is clearly wrong, but saying that it's wrong and right is not very informative. For example, recall our earlier example of the confidence 0.22, 0.6, 0.18 versus 0.32, 0.36, 0.32. These will output the same argmax. So in both of these examples, this one is just as this is the highest value, the second index is the highest value, and this one, the second index, is also the highest value. But you can understand how this one may be, quote unquote, more right. Like, for example, if the second index was the right answer, this one is more right than this one. And so that's what loss is coming to do. Loss needs to tell us that information. And so he says, but are these two examples really as accurate as each other? No, they're not really as accurate as each other. This one is far more confident that the second index is the correct class. And because of that, it may be more right or more wrong. So that's why we use loss. And the loss that we're going to use is categorical cross entropy loss. If you're familiar with linear regression, then you already know one of the loss functions used with neural network that do regression, squared error, or mean squared error with neural networks. This is a kind of loss, squared error or mean squared error, very similar but not the same, that is good for linear regression. It's good for linear problems. But for classification nonlinear problems, you really need something else, and categorical cross entropy is the most commonly used one. We're not performing regression, okay, fine, so therefore we're going to use the categorical cross entropy. The model has a softmax activation function for the output layer, which means it's outputting a probability distribution. I think that is explained. Categorical cross entropy is explicitly used to compare a ground truth probability, or y. So we're comparing the y, which over here, these are the y's. We're comparing this with some predicted distribution, y hat, which I've never seen before, or predictions. So it's basically comparing the target and the prediction. So it makes sense to use cross entropy here. It is also one of the most commonly used loss functions with softmax activation on the output layer. The formula for calculating the categorical cross entropy of y, actual desired distribution, and y hat, predicted distribution, is this. It is the negative sum of all y times the log of y hat. So actually we're going to simplify this quite intensely, and also it may look complicated, but as I showed with the softmax activation function, things may look complicated in math, and then when you program it, it's actually very intuitive. So let's see, we're actually going to simplify this, and once we simplify it, it's going to look more like this. It's going to be the negative law of y hat. Literally, that's what it is. There's nothing else. Where k is an index of the true probability. So you'll see exactly what this means once we start coding. Okay, so let's take a look at the actual code, and let's bring some real examples here. So let's go to main.go, and let's comment out all of our code so that we could start playing around and get a sense for how the categorical cross entropy loss works. So imagine we have some softmax outputs. Let's call it softmax outputs. Colon equals a list of float 64. 0.7. Okay, so I'm going to copy these values. I get to copy them because I have the book. If you want to copy them, you should also buy the book. Highly recommend. Great. Okay, so imagine we gave a neural network an input, a picture, for example, and it gave us this probability distribution as to what class it thinks the picture should be. Okay, so this is the softmax output. Let's pretend that this is the output of our layer. Okay, now we have 3 class confidences in the above output. There are 3 possible classes. And let's assume the desired prediction is the first class, index 0, which is currently 0.7. So let's assume that the neural network is actually right, the model is correct, and the desired class is the first index, is the 0th index, index 0. If that's the intended prediction, then the desired probability distribution is 1, 0, 0. This is the desired, like in an ideal world, this is the probability distribution. It is 100% confident that's the first class, and no confidence for the second ones, for the others. Cross entropy can also work on a probability distribution like this. They wouldn't have to look like the one above. In other words, it doesn't have to look like... I don't know what he really means by this. He may mean that it could also work in one where the 0th index is not correct. Like in this one, the model is correct. Cross entropy could also work when the prediction is incorrect, which is important. That said, the desired probabilities will consist of a 1 in the desired class and 0 in the remaining undesired classes. So there's 1 in the desired class and there are zeros in the remaining ones. Arrays or vectors like this are called one hot, meaning one of the values is hot, on, with the value of 1, and the rest are cold, off, with values of 0. When comparing the model's results to a one hot vector using cross entropy, the other parts of the equation zero out, and the target's probability loss is multiplied by 1, making the cross entropy calculation relatively simple. This is also a special case of cross entropy calculation called categorical cross entropy. To exemplify this, we'll take a softmax output, this, and targets 1, 0, and we'll apply the calculations as follows. So this is the equation for loss. By the way, I read through that very quickly because I really think it's explained more just by the diagrams and eventually by the code. So let's take a look. This is the calculation for the loss. Broken up, this will be -1. So everything is going to be negative, -1 times. So it's just the negative of 1 times the log of 0.7 plus 0 times the log of 0.1 plus 0 times the log of 0.2. Why are these the numbers? Well, it's the first index times the log of the second index plus it's the first index times the log of the first index, the second index times the log of the second index, the third index times the log of the third index. And as you can see, it's y times the log of y hat. It's the correct thing times the log of the prediction. And the I and the j are just indexing terms. And this all simplifies to negative 0.367 blah, blah, plus 0, because 0 times that is 0, which equals this. Now notice, why is this going to be simplified a lot? Well, 0 times anything is just 0. 1 times anything is just that thing. So really, this whole thing simplifies to the negative of the log of the predicted percentage for the correct value. So this is the correct value. This is what the 0th index is the correct index. So we get the log of the correct index in terms of the predicted output, and then we make that negative, and that's our loss. Okay, so now he's going to code it for the first time. So let's also code it, and let's follow along. So he has target output, which he has set to that. So let's see, target output, colon equals, and this is going to be something very similar, float 64, 1, 0, 0, great. And now let's see, loss, colon equals, parentheses, and let's make this negative. You cannot forget the negative. The negative is crucial. So this is going to be math, and you're going to have to import math above, as you can see over here, math. So math dot log of softmax outputs index 0 plus, not plus, times target output index 0 plus, and we're going to have to do this 2 more times in our specific example, 1, 1, 1, 1. Great. Okay, so this is our loss, and then we could fmt.print loss, fmt.print here, and there we go, loss. And we should get the same value that he got, if we did it correctly, of course. So let's run this, and let's check it out. Great, so we get the exact same output that he got, and that's how you calculate categorical cross entropy for one sample. So that is the full categorical cross entropy calculation, but we can make a few assumptions given one hot target vectors. First, what are the values for target output index 0 and target output index 2? This is exactly what I said. They're both 0, and anything multiplied by 0 is 0. Thus, we don't need to calculate these indexes. So we could just not calculate these two, because both of them will just evaluate to 0. And we're just adding 0, which is not important. So we get rid of both of those, and we're left with this situation. Okay. Next, what is the value for target output index 0? Target output index 0. It's 1. So this can be omitted as any number multiplied by 1 remains the same. So very good. The same output then in this example can be calculated with loss equals the negative math.log of softmax output index 0. So let's get rid of this, and you're going to see something very interesting. If we get rid of that, and we get rid of this, great. This will be correct, but one thing that's interesting is, look, we're not using target output. That's weird. You would expect target output to be important in the loss calculation. And guess what? It is. It is important. Don't be tricked. This is very important. And you know why it's important? Because how did we get this number, this 0 over here? How did we know it was supposed to be 0 and not 1 or 2? The answer is because this is the highest index. It's the argmax of target output, and that's why we put the 0 here. That's why this one is the logarithm that we're calculating. So for now, we could comment this out. And if we run this, we will get the exact same number. Ta-da! Same number, right? Very cool. Okay. As you can see with one-hot vector targets or scalar values that represent them, we can make more simple assumptions and use a more basic calculation. What was once an involved formula reduces to the negative log of the target class's confidence score, the second formula presented at the beginning of the chapter. As we've already discussed, the example confidence level might look like this or this. In both cases, the argmax of these vectors will return the second class as the prediction, but the model's confidence scores about these predictions is high only for one of them. The categorical cross entropy loss accounts for that and outputs a larger loss the lower the value of confidence is. Okay, so let's take a look. He's already done this and we don't have to do this. Let's just take a look. If the model outputs a 1, in other words, I'm 100% sure that this is the class and it's correct, then the loss will be 0. As you get less and less confident, the value of the loss goes up and up, but it becomes negative. So the way we get rid of the negative is we make it negative. We put the negative here. And that's how we get rid of the negative. But you can see that as it gets less and less confident, so imagine if it was only 1% confident that the class it was guessing was the correct class, then this would be the loss, which is a pretty high loss. Okay. We've printed different log values for a few. Okay, so he's already done this and he explained it, and very good. Now, one thing that's interesting is we're gonna have an issue with math.log of 0. We're gonna have to figure that out, and we'll explain that. Okay. So far, we've applied log to the softmax output, but have neither explained what log is nor why we use it. We will save the discussion of why until the next chapter, which covers derivatives, gradients, and optimizations. Suffice it to say that the log function has some desirable properties. Log is short for logarithm, and is defined as the solution for the x term in an equation of the form a to the x equals b. For example, 10 to the x equals 10, 10 to the x equals 100 can be solved with a logarithm. Which logarithm? Log base 10 of 100 equals x, which evaluates to 2. 10 to the power of 2 equals 100. This property of the logarithm is especially beneficial when e, Euler's number, is used as the base, where 10 is in the example. The logarithm with e as its base, so in other words log base e of whatever, is referred to as the natural logarithm, natural log or simply log. You may also see this written as ln of x, or log of x, or log base e of x. The variety of conventions makes this confusing, so simplifying things, any mention of log will always be natural logarithm throughout this book. When we type in log here, we mean log base e. The natural log represents the solution for x term in the equation e to the x equals b. For example, e to the x equals 5.2 is solved by log of 5.2. And he demonstrates that over here. And you can see that by raising it back, e to this number equals 5.2. The natural log of 5.2 equals this number. Let me turn on the air conditioner real quick. Okay, onward. So that is what logarithm is. The small difference in the result of the floating point precision is Python, so you see how this is not exactly 5.2, that's just a rounding error. Okay. Great. Getting back to loss calculation, we need to modify our output in 2 additional ways. So this is too simple, we have to do some modifications. First, we'll update our process to work with batches of softmax output distributions, and second, make the negative log calculation dynamic to the target index. So as you can see, we're hard-coding in the index, we have to make that dynamic, and we also have to handle for batches, which will be 2-dimensional, not 1-dimensional. Okay, so let's do this. Consider a scenario with a neural network that performs classification between 3 classes. So there are 3 classes here, which means there will be 3 numbers in each of these. Great. And the neural network classifies in batches of 3. So we have batches of 3, which is why we have 3 outputs here. Sorry for the air conditioning, it's broken. I say that in every video. Okay. And the neural, okay, after running through the softmax activation function with batch of 3 samples and 3 classes, the network's output layer yields this. So imagine this is the output. So let's code that in. This is not going to be 2-dimensional. And let's make this bigger. And I get to copy, which is awesome. Copy, and over here, paste. Great. Let's bring these guys in. You have to add a comma here. We got to get rid of these brackets, as you can see. Let's make this open, and I can't just do that. I gotta actually move. Great, and let's make these close. So great. So these are the outputs of our layer. Excellent. we need a way to dynamically calculate the categorical cross entropy, which we now know is a negative log calculation. To determine which value in the softmax output to calculate the negative log from, we simply need to know our target values. Okay, so we need to know what we should have gotten from our neural network. In this example, there are 3 classes. Let's say we're trying to classify something as dog, cat, or human. A dog class will be 0 at index 0, a cat class will be 1 at index 1, and a human class 2 at index 2. Let's assume the batch of 3 sample inputs, so let's assume that these inputs to the neural network is being mapped to the target values of dog, cat, and cat. So it should have outputted dog, cat, and cat. Instead, I think it outputted a dog, cat, and cat. So no, it got it right, I think, which is good, but we're going to have to calculate the loss. So the targets as a list of target indexes will be 0, 1, and 1. So this is not one hot encoded. This is just a list of what should it have been. It should have been a 0, so the first output should have been a 0, it should have been a 1, and it should have been a 2. This looks very similar to our situation, the raw y. It should have been a 0, it should have been a 0, it should have been a 0, forward and forward, it should have been a 1, it should have been a 2, exactly. So let's do that. So the target output should be 0, it should have been a 0, it should have been a dog, it should have been a cat, and it should have been a cat. So this is not one hot encoded. One hot encoded would be 2-dimensional in this case. Okay. So these are the class targets. In fact, let's call it that. Class targets. And great, class targets. Okay. The first value 0 in the class targets means that the first softmax output distribution intended the prediction was the one at the 0th index. So this is the one that we're going to be looking at. The model has a 0.7 confidence score that is observed as confidence score that this observation is a dog. This continues throughout the batch, where the intended target of the second softmax distribution, so these guys, the second one, was an index of 1. That was the intended one. The model only has a 0.5 confidence that it was the intended thing. The model is less certain about this observation. Great. In the last sample, this is also the second index from the softmax distribution, a value of 0.9. In this case, a pretty high confidence. With a collection of softmax outputs and their intended targets, we can map these indices to retrieve the values of the softmax distribution. So let's do that. We're gonna do a for loop. Okay. Let's actually say loss is : equals. I'm gonna structure this a little bit differently than the way he did it. It's gonna be a list of float 64s, and we're actually gonna use make syntax. Make a list of float 64s. And we're going to have just as many losses as we have classes, so as we have class targets, as you hear. So let's make the length of class targets. Because for every single target, we're going to have a loss as to how close did it get to that target. So that's going to be the length of the losses. And let's say for I, comma val, : equals the range of softmax outputs. So we're going to loop through softmax outputs. We'll say losses at index I equals the negative of math, and again you're going to have to import math.log of the value. No, sorry. Here, okay, so this is not value. These are, each one of these will be a list, a slice. So we're going to have to say, I don't know, let's call these preds, like predictions, preds. So equals preds at the index. Which one should this be? Well, this should be class targets at index I. Class targets at index I. And this is a float, so this needs to be converted to an int. So why is it class targets at index I? Well, for the first one, when I is equal to 0, we want class targets at index I, which is the 0th index. We're going to use that. We're going to use this 0 to actually index, oh, not class targets, sorry. We want to index preds. Great. We want to index preds. Okay. So we're going to use the I to index, oh, no, sorry. We're going to use the I to index class targets. In this case, so for example, for the first time, when I is equal to 0, in other words, we're looking at these, the class targets at index I will be 0, and we're going to use that 0, class targets at index I, to index the preds. And the preds will be this. So preds index 0 will be 0.7, and we'll get 0.7, we'll do the negative math.log of 0.7 to get the first loss at index 0. And that will, and then we could print losses. And so that will go dynamically through each one of them. And so we'll get the correct loss for each one. All right, let's see what the losses are. Oh, so first he's just printing out the distribution at the target. Okay, so first he's just printing out the values. So I could actually show that we're getting the correct values as well. Hold on. Let's comment that line out. Actually, no, let's not comment that line out. Let's comment this line out. And for now, I'm going to print fmt.println the preds at index. This is what it is. The preds at index. The int of the class targets at index I. So let's see, and we should get the same values as he is, 0.7, 0.5, 0.9, 0.7, 0.5, 0.9. In fact, I'm going to actually make this a variable, value colon equals that. And then over here, I'm actually just going to pass in value instead to make it look a little cleaner. Great. So, yeah, he's actually able to turn this into a NumPy and index things a little bit cleaner, which is very nice for him. We're not able to do that, so we're gonna have to do it in our tensor package, but not yet. We'll save that for a little bit later. I think I found a way to do that. Okay. So he's just showing how the indexing works, and he's ranging over it, and he's showing that he could get it. And this is all NumPy, so we don't have to look at that. And then he's actually calculating the loss using NumPy syntax. So let's also calculate the loss, and let's print out the loss. And we should get these values as well. Okay. Great. So we are, in fact, these are the same values, as you can see. 0.3566, 0.3566, yeah, very good. 0.693, 0.693, 0.105, great. So these are the same values. So we're doing it correctly. Finally, we want an average loss per batch to have an idea of how our model is doing during training. So instead of having these three outputs, we want to have an average. We want to get the average of them, so that we can return that as the loss. So as right now we have losses. We want like loss. What is the loss? And we're gonna get that. So he's doing that via NumPy because he has NumPy.mean, and he could just pass in the loss, and so he gets the mean. We're not able to do that, so we're gonna have to do that. So let's do that now. Let's convert everything to tensor format right now. So let's import tensor. We're gonna import gorgonia.org /tensor. Great. And then over here we're going to change this to softmax backing, because we're actually make this into a tensor. So the way backing works, it has to be one-dimensional, and we're going to get rid of all these brackets. Get rid of all those brackets, and also we're going to have to get rid of this entire for loop, and also the losses. Okay, so now that we have the backing, we're going to say softmax outputs. What will the actual outputs be? It's actually going to be a tensor. Softmax outputs colon equals t dot new t dot with backing, softmax outputs backing, and the shape t dot shape. Sorry, hold on. Let's actually expand this to make it cleaner, and so we could see all of it. So the next argument will be passed in will be t dot with shape, and this will be 3 by 3. It's going to be a shape of 3 by 3. Great. Softmax outputs colon equals t dot new t dot with backing. Excellent. Okay. So now that we have the softmax outputs as a tensor, we should figure out how to calculate the loss from it. So let's say here. I don't know, should we call it like y hat? Should we call it predicted? Let's say predicted vals. Predicted vals colon equals a list of float 64. I'm only showing this because when we're actually learning how to code this, when we're actually learning how to code this, we're going to have to learn how to take in the output from the neural network, which will be in the form of a tensor. So we have to learn how to calculate the loss from the form of a tensor. And we're going to be switching back and forth between Golang objects and tensor objects, but just follow with me. So the predicted values will be a list of float 64s. And in fact, really, we should just get predicted vals backing, which will be a list of float 64s. How long will it be? Well, it will be, we'll have a value for every output, for every probability distribution that we have for every one of these. we're going to get one value. So how long will this predicted vals backing be? How many of them will we get? Well, we'll get one from this, and one from this. So 3. What is that? That is the softmax outputs backing, not the softmax output backing, the softmax outputs dot shape at the index of 0. It's the first index of the shape. And so I'm trying to make this dynamic, which is why we're passing the length in like that. Okay. Now we have to iterate over the softmax output dot backing, and we're actually going to use the class targets over here. So let's make an iterator. I learned how to do this yesterday. So it colon equals softmax outputs dot iterator, and this gets us an iterator which we can use. This will allow us to iterate over the softmax output backing. So this is the syntax for doing that. For let's say I comma error colon equals it dot begin or start. Yeah, start. As long as the error equals nil. So that's our condition. As long as the error equals nil, we should do something, and then at the end we should say I comma error equals it dot next. So that's the syntax, and this will be a for loop basically. And just to show how this works, I'm going to say print. I'm going to say fmt dot println I. Let's print out the I. Let's print out. One thing that we're going to need is the coordinate. Like, what is the coordinate that we're currently looking at? So that the way to get that is it dot chord. And then we can actually get the actual value. So let's say it dot. I'm sorry, not it, but we'll say softmax outputs. Yeah, softmax outputs dot at it dot chord dot dot dot. And oh right, so this is gonna have to return like a error. So let's say val comma underscore. We don't really need a handle for the error right now. Colon equals this, and then we're gonna print out the val. Okay, great. You might want a handle for the error, by the way. So we have an error. We have a bunch of declared things that aren't used. So let's comment those out. Let's run that again. Basically, what I'm trying to do is I'm trying to separate out. So this is actually funny. It goes 0, 0, and then like the 0, 0 index. This is 0.7 is actually the last one given, and it starts off at 0, 1, which is this. So you see how it's iterating over all of them, and we get the coordinate, and I basically corresponds to which value we're currently looking at, and we get the coordinate, and we could get the value at the coordinate. So the reason why I'm doing this is because I want to move everything into the predicted vals backing so that we could make this into a tensor, so that we could just get the logarithm of that with one call with the tensor library. I'm going to turn off the air conditioning now because it's making a noise, and it's annoying, and it's cold enough that I think I can handle myself for a while. So let's continue. Okay, so now we have to figure out which of these are supposed to go into here. Which of these do we want to get? Like these will be the things that will be logged, that will be logified. So great. So how do we determine which of them? Well, we want 0, 0. For the first one, we want 0. Why? Because this is 0. For the second one, for the second probability distribution, we want the 1. So that's going to be 1, 1. For the third one, for the second value, we want also 1. So that's going to be 2, 1. Well, the great way to say this is actually an if statement. So let's actually get the coordinate. So c colon equals it dot chord. We're going to work with that. And we can say, so this is a for loop. I'm going to actually make some space here. And we don't actually need I, funny enough. So let's just make this an underscore. So now we could say if c index 0 equals. So if c index 0, which will be like, it's either going to be 0, it's going to be 1, if it equals the class targets, and in fact, let's move this thing up because all of this is basically populating. This entire for loop is to populate this list. So if it equals class targets index c index 1. So if this is the case, then that is the value that we want to put into here. Why? Well, let's take an example. When c is 0, 0, when it's the first c, essentially, when it's the first coordinate, then c index 0 will be 0. So that means class targets index C index 1, so that's going to be 0 as well. So this will be class targets index 0, which is the first class C index. Hold on. Hold on. I'm sorry, no. I messed this up. Class targets index C index 0. So this will be, like, when we're looking at the first probability distribution, this will allow us to look at the first value. When we're looking at the second probability distribution, when C index 0 is 1, when C index 0 is 1, that means we're going to be looking at this one. When C index 0 is 2, that means we're going to be looking at this one. And so then if this value, which is going to be either 0, a 1, or a 1, equals C index 1, then that is the value we're looking at. So when it's 0, 0, that is the correct one because the class targets will be 0. And so 0 equals 0. This 0 is going to equal this 0. This value over here, which is this value, is going to equal this value over here, which is this value, which means that this is the one we want to look at, which lo and behold is correct because we want to look at this one, which corresponds to the 0th index. And you can run it through it in your head, and this will work for all probability distributions. We'll get the correct value this way. And I could actually print this out. So let's say fmt.println. What will this be? This will be, well, what's wrong here? Invalid operation, can I compare that mismatch types float 60? Okay, so let's just change this to let's change this one to a float. Why not? Float 64. Great. Println, we want to get the softmax outputs dot at the chord, the C, which was just C. Dot. Yeah, dot. Great. This one we could still comment out for a second. And let's print this. Let's run through this, and we'll see. We'll get 0.7, 0.9, and 0.5, 0.9, and 0.7 again because we do the first one last for some stupid reason. But you'll see that doesn't actually make sense because I'm going to use C index 0 as our indexing value when we populate this slice. So okay, now that we get the correct value, here we'll say val comma underscore. We don't really need the error. Colon equals softmax outputs dot at C dot. And this doesn't need to have a capital T. So this is going to return an interface, actually. Yeah, this is going to return an interface and an error. And we don't want an interface. We want a float. So let's actually make this here. Here, we'll call this temp val, because I want the actual val to equal temp val dot float 64. We want to get the actual float 64 of that interface. And this should work. Normally you'd have to like handle to make sure that you could do this, but we know we could do this because we're getting it from a tensor with type float 64. So we know we can do that. So now that we get the correct value, we want to put that into our predicted vals backing. So let's put that into our predicted vals backing. Now how do we know which place to do it? Okay, so predicted vals backing index, what's the index? Should equal val. So we need to figure out what the index should be. Well, the index should be C index 0. For example, when C index 0 is 0, that means that we're looking at the first probability distribution, which means we want the first value. We're trying to get the first value. When C index 0 is 1, that means we're looking at the second probability distribution, which means we want to put this into the second value of predicted vals backing, and so on and so forth. So this works. And again, you should look at it like yourself if you don't understand it, but I'm just trying to show that it works, and take a look and play around and print things out. You really should get an intuition how this works. This is real like dynamic programming, and sometimes it can be confusing. So it's okay if it's confusing, but I can't really explain it any more than I already have. You really have to just sort of play around and get an intuition for it. And play around, it's fun. So let's print out the predicted vals backing, because now we've populated our predicted vals backing, and we get all the, here, now we have all the values that we want to log. So great, so now we have the backing. That was all just to get the backing. Now we can actually turn that into a tensor and then log it. So let's say here, predicted vals, not backing, but predicted vals, colon equals t dot new. And this will be t dot with backing, predicted vals backing. And we don't have to pass in a shape over here because we want it to be one-dimensional anyway. And now let's get the log of that. So losses, colon equals t dot log of predicted vals and this is actually going to return an error as well, so we should handle for that. Can I just do ml dot? Nah. Do I have a function handle error? No. Okay, fine. So hold on. So let's go into our machine learning place, and we have maybe an add biases. Do we have a function to handle error? No. Do we have an activation, so function to handle error? No. We have it in dense layer. Great. Let's copy this function to handle an error because I just don't want to code it again. Let's go back to main.go. Let's close this back and let's paste this function over here. And we have to, okay, you know what, instead of importing log here as well, I'm gonna do something else. Here, in ML, in the dense layer, we're gonna change this to be capital so that we could access it. And then we're gonna have to change everything else to capital as well, which is actually a little bit annoying now that I think about it. You know what, fine. So since I'm gonna have to do that, and I don't wanna go through all that, I will actually just copy the function. I had an idea, and I decided not to do it because it would have meant a little bit of tedious work, and that's just how I roll. So we're gonna have to import log as well. Do that up here. Log. Great. Okay, now we have a function for handling the error. All that was just so that I could handle error and then pass in the error here. Great. And now that we're doing that, let's also say that this is an error, and we should handle error, error. And do we have any other places? No, not here, not here, not here. No. Okay, great. Okay, so losses equals the log of that. Let's print out the losses. fmt.println losses. Now, you're going to say, Alicia, we already have that. We already did that. Oh, hold on. We want these to not be negative, right? So we're going to have to multiply that. So let's say losses, comma, error equals t dot mul. Yeah, I guess we're going to have to mul. And we're going to multiply, and this could take in a scalar, which is nice. I wonder, yeah, we're going to have to multiply the losses by, we can't just pass a -1, it has to be a scalar. So t dot new, this is very silly, t dot with backing, and this will be of type float 64, -1, and there you go. So this is like a scalar. And we can use that to multiply the losses so that we get the proper thing. I believe this will work. And let's also come over here, copy that, and put that over here. Great. Okay. Let's run that. I believe this should work. Yeah, okay, that works. So you're going to tell me we already had these values. Why did we go through that whole thing? Well, the answer was because now we have it in the form of a tensor, whereas before we had it in the form of a list. So great. So now we have it in the form of a tensor. And these are the same values as him. So now he wants to average it. We want to get the average loss. What's the average of these things? So we can figure that out. The best way to just get an average, well, he has a function that could do it. I don't think that we have a function that could do it. Let's see. T dot mean. No. T dot average. T dot geometric mean. No. So I don't think that we have a function to do this. So we're going to have to do this by ourselves, which is fine. Okay, so what is he doing? Well, we want to get the sum of all of these and divide it up and divide it by the length of all of them. So we can do that. Let's do it. Sum colon equals t dot, I guess it's sum. Yeah, we have a sum. We have a sum function. Great. Sum of the losses. And this also returns an error, so we're going to have to put that over here. Error and handle error. Great. Let's put this all over here. Calc losses. Great, so now we have to handle the error, and now that we have the sum, we want to do, sum is in the form of a tensor, by the way, but it's really it's like a scalar, it's like a 1 digit. So let's print out the sum. fmt.print, just so that we know what we're dealing with. Sum. Great. We don't really need this anymore. And sum is in the form of a tensor, right? So great. So this is the sum of all of the losses. And now we want to do t dot divide the sum by, so now we need an interface. It needs to be like a scalar. So I wonder, we could probably just do the size of losses. So losses dot size, I think, right? Yes, size. Great. And this returns an int, which is unfortunate because I don't think that it'll accept the int. So let's actually just try this. I don't think this will work. I think it's going to return an error. So let's print that. And let's get rid of that, and let's put the parenthesis around here. Okay, yeah, this is probably not going to work. I already know why it's not going to work. The reason why it's not going to work is the same reason why we had to do this banana thing up here. Yeah, div failed expected scalar to have the same data type as the tensor. Instead got an int. Great. I wonder if we do like float 64. Because it's complaining that it's not the right data type. So maybe turning it into a float 64 would help. Oh, it worked. Okay, great. So actually, I think that we can do the same thing up here. We don't need to do this. I think that we can get rid of that, and we can, oh my god, that's crazy. We can just say float 64. I'm sorry, I thought that the only way to fix that issue was to make it into a tensor. I was wrong. Yep, still works. Okay, great. So this is our loss. So let's put this over here. So instead of saying losses, now we actually have a full-on loss. Loss, comma, error, colon equals this, and then we can handle the error, handle error, error, and finally we can fmt.print ln loss. Great. And great. So this is our value. Is it the same as his? It is the same as his. Very good. In fact, it's exactly the same as his. Wow. So there you go. That is very cool. Okay. One thing that we need to do, which is what he's going to do right now, is actually make this a little bit more dynamic. So what we have right now is it's working off of this format for the class targets. But what if class targets was in the form of one hot encoded? So instead of looking like this, it instead looked at like this. And let's expand all of this. So this is 0, 1, and 1. So here, let's take a look. So since it's 0, it'll be 1, comma 0, comma 0, and this one will be 0, comma 1, comma 1, 0, sorry, and this one will be the same thing. Okay, both of these represent the same information. You understand? Both of them represent the same exact information. The difference is this one is multidimensional and it's like one hot encoded, but it's the same information. This one's showing that the first class is the correct one, and this one's showing that the first class is the correct one. So how do we make it dynamic so that it could both, so that our function, I guess it's a function, because we haven't really made this into a function yet, but one day we're going to make it into a function, right? How do we make it so that it's dynamic and it can handle both one hot encoded and non-one hot encoded? Well, he's doing that, and he uses a lot of Python tricks, and it's very fun and very clever and whatnot. We're going to have to do something different. What we're going to do is the only time that this is important, the only time that this distinction is important is in this loop, right? Because it's right here on this line is when things get messed up. So let's make an if. Let's make an if statement. If the he has like a dot shape. If, by the way, y values, like so now because of how we're coding this, the y values are going to have to be Golang slices. We're never going to be able to use tensors, at least not the way that I've set this up. And if we do use tensors, we're going to have to change how the loop works, because right here things will go different. So for now we're using Golang tensors. So we could say if how do we do this? Is there a way to tell the type of, because he's using the dot shape. He's saying is the shape 1 or is the shape 2? But unfortunately this doesn't really have a shape. So if class targets dot, if class targets index 0 equals int, like that's kind of what I want to say, dot, I think this is how you do it. Dot type, yeah, equals int. I believe this is the case. No. However, it is not an alias to say int32. Int type is not an expression. How about we say if it equals float 64 dot type. I think this would probably work. No. Okay, inval operation, float 64, literal value of type float 64 is not an interface. So no, so this only works for interfaces. So let's actually make a quick Google search. How to tell the type of a variable in Golang. Different ways to find the type of variable in Golang. I guess I've looked at this before. No, I don't want to print it. I want to actually use it. I guess you have to use reflect. No, I don't want percent. So we have to do reflect dot type of. Okay. If reflect, so that's a package that we're going to have to import. If reflect dot type of the class targets index 0 equals reflect dot type of float 64. Oh, sorry, 0.0, which I guess will be a float 64, right? Yeah. So if the first index is going to be like that, if the first value, which in this case is a float 64, equals a float 64, then we should do our old loop like this. And we should go like that. Obviously, this is going to return false right now, but if we get rid of this and we put it like that, then you know what? How about we do something else? How about instead of doing this if statement, what we do is we keep. I have a great idea. We keep our loop. We'd have no if statement, and we basically say that if it's one hot encoded, we're going to turn it into something else. So, and we're going to have the if statement up here. So if it's one hot encoded, we'll turn it into the format of this. So class targets, and we'll say I don't know what we should call it though, is the thing. We'll say, okay, first things first. If class targets, if reflect dot type of class targets index 0, so we're going to have the same if statement, equals reflect dot type of this is weird. I'm actually just now realizing, still contemplating Go versus Node.js. It's a great contemplation. Personally, I don't do much web development, but I love Go. So if I could do web development, I would do it in Go before anything else. I just have to figure out how to do this because we're gonna have to make this into a function, and the problem is Go is just not as dynamic as Python is. Like Python's able to treat very similar things very, very well. You know what? The best way I can think to do this is actually instead of we're gonna make it that our program handles it as tensors. So class targets backing, and over here backing. Yeah, so our program should expect a tensor at this point. So we're going to make this into a tensor. Class targets colon equals t dot new from here t dot with backing class targets backing. And in this case, we don't really need a shape. We do not need a shape in this case. So now we can come over here, and we are going to make it a for loop question. So we're going to make it something very similar to how he has. If class targets dot shape, which will be a slice, right? So dot shape. This is not supposed to return a AP. I mean, does this work? X0 equals 1. Does this work? Yeah. But can I do the length of this? No. Shape. Does this have dot dims? We could just do dot dims. So if the amount of dims equals 1, or yeah, 1, if it's one dimensional, then we'll set it up like this. Except when we index things, we're going to have to get it a little bit differently. So instead of class targets index, we're going to have to get the we're going to have to get the here correct answer, correct val, correct index colon equals class targets dot at, and then this needs to be, so what will the coordinate be? Class targets dot act. What will the coordinate be? The coordinate will be C index 0. And then of course class targets dot act. Yeah, this returns an interface and an error. So comma error. And then we want to handle the error. Error. This is all, it's not auto-completing because there's an error here. So if correct index equals the coordinate index 0, this is an interface. For some reason we are able to compare it. I'm not sure why, but whatever. And we didn't need that package. We didn't need reflect. Okay. So this should still run the way it ran before. Let's just make sure that this is working. I just set this whole thing up so that it would run the way it was before, because this is the same format that we had it before. And now we're just checking to see if it's one hot encoded. And we're seeing, like, if it's not one hot encoded, do it the old way. But the old way in a new way. Oh, so this, it worked. Wow, it worked. I didn't think that it would work on the first try. Cool. So that worked. Now let's do it the other way. If else if class targets dot dims equals 2. So now if it's one hot encoded, what's the problem here? Can I convert type int to func? Else if class equals 2, then we'll do a very similar situation, except we will say that we are looking for correct index comma error colon equals class targets dot at C index 0 comma the this is going to be complicated because in this case we really need to be able to work with multi-dimensional things, and I want to get the argmax of the first value. So I want all the argmaxes. So t.argmax, I'm sure there's an argmax of, in this case we want class targets. So but actually before the for loop I want the argmax of class targets. What's this? This takes in a tensor. Class targets is a dense. Oh, and I'm sorry, hold on. And the dimensions that I want, the axis is going to be the first, I believe. So now just with that, I actually want to comment all of this out and comment all of this out, and I just want to make sure we can code this properly. So let's come over here, and I want to make sure we're getting the correct argmax. So let's say fmt dot print ln fmt dot print ln, and this returns an error. I imagine in a tensor, right? Yeah. So argmax comma error colon equals, and then we'll handle the error, handle error, and then I want to print ln the argmax. But in order for this to run, I also have to make it like this. So I have to get rid of that backing, and I'm going to make it like this backing. And now we do need to pass in a shape. The shape will be t dot with shape, and this will be 3, 3, 3, 3. Okay, and then okay. So now that that is the case, now that it's two-dimensional, this will run, and so we'll get the argmax probably. So let's see. Or all of the argmaxes. So great. So the first one is 0, 1, 1. So great. So basically we just converted everything to be, to be in this format, right? This line right here, the argmax converted all to be in this format. And now we can actually do things in the exact same way as before, because this is a tensor. But over here in these lines of code, instead of saying okay, so we're gonna do a very similar operation here. We're gonna get the correct index in the same way, except we're gonna say not class targets, but rather argmax. Oh, let's call this argmaxes, and let's call this argmaxes. What's the problem? Argmax declared but not used. It is used. It's used right here. What is the problem? Something somewhere got very confused. Sometimes this happens with Go, where the compiler is like, wait, does all of this make sense? I think all of this makes sense. Yeah, okay, all of this makes sense. And now we just have to handle for the error over here. Handle error. And okay, everything should work. We basically just converted it all using this argmax. We got these as a tensor, which was the same as this was, right? And now we should get the loss. So let's go over here and let's print out the loss. Infinity. Okay, so that's not good. Yeah, that's problematic. I don't know how that happened. You got the correct index. Argmax is .at c index 0. If correct index, let's see, let's try this fmt.println correct index. I'm not sure what went wrong, is the simple truth. I think everything should be working the same way as it was before. This is confusing. 0, 1, 1, 1, 1, 1, 1, 0. That's weird. I don't know why this is happening so often. I mean, I'm not sure why this is happening. In truth, I'm not sure. 0, 1, 1, 1, 1, 1, 1, 0. Why is this even running so often? The correct index in the beginning is 0, and then it's 1. fmt.println argmaxes. I'm not sure why the iterator is going on for so long. If correct, okay, so obviously this, no, so that should have been printing just as often as it was. I'm sorry, that wasn't the best way to do it. Let's say fmt.println correct index over here. This should print out like 0, 1, 1. Yeah, 0. No. Okay, so hold on. So, okay, we got it. This if statement is never returning true for some reason. So, yeah, this if statement is never returning true. This print statement is never getting run. Right, okay. Leaving, yeah, so at some point, I guess we divide by 0, which is infinity, I think. So for some reason this is never getting run. I don't know why. Correct index colon equals argmaxes dot at c index 0. If correct index dot float 64. Is that the issue? Interface is int, not float 64. In this case, okay, in this case it's returning a tensor with the type of int, which means that this is a float 64, which means it's never getting shown as true. So if I changed this to an int, then this would work, I imagine. Go run. Right, okay, so that works. Now, I don't want to change this to an int. I would rather both of these loops look very similar, because I think that at some point when we're making these into functions, we'll actually be able to make this stuff very dynamic and very, very clean. So I want to actually just make this of type float 64. So argmax dot type, or argmax dot change type, set type, argmax dot, I don't know, value, no, argmax dot not transpose, right, 0, no. T dot float argmax dot, maybe I could like multiply it. Maybe I can multiply them. T dot mul argmax. No, I'd have to make it an integer. This is a silly issue because it is working. The problem is this if statement will never evaluate to true because, so maybe I can make this into a float 64. Float 64. Maybe I can make this into a float 64. I wonder. No, I'd have to say float index dot. No. If correct index equals float 64. I really would like argmax to just be float 64 instead of being ints as they are. Argmax t dot change, no, t dot set type argmax dot type. I keep on doing that. Argmax dot data type argmax t dot data. I guess maybe I can make a new argmaxes equals t dot new t dot with t dot, I don't know, sorry, this is t dot of float 64. I wonder if you could just do a backing t dot with backing. I wonder if you could put a backing as a tensor argmaxes. I wonder if that works. I'm not sure. Let's see. No, you definitely can't. Okay, fine. Expected a slice. No. Okay, that's slightly annoying. Yeah, this is unfortunate. So what if I change this to an int? if I changed this to an int, then this worked, right? Yeah, then that worked. What if I went up here and changed this one to an int? I don't think that that worked, right? So I can come over here, and I can, and in order for that one to run, though, we're going to have to change this to be like this, and we're going to have to get rid of the shape. And so now this one should run, although it's probably not going to run correctly. Yeah, so that's getting positive infinity because this is never, now this one's never evaluating to true. Very unfortunate. Okay, so there's no real way to make these if statements look exactly identical, and honestly, honestly fighting for it is a little bit not important, because it does run and it works, but I do kind of want it to be exactly the same, because I imagine I could make this into its own function. Like maybe we could have multiple functions whenever we make this into a class, and we'll have a function to to change things if one of them is like one hot encoded, and then we can just call one function for this entire for loop, and that way the code will be cleaner. But okay, I'm going to look into that. I'm going to continue looking into this more, but I think that this is the end of today's video. And the next time we're going to start working on fixing some problems in here, because there are a few problems that we really need to fix. Otherwise, we're going to have errors later and down the line. But that's it for today. I'm going to keep looking into this issue and see if I can find a solution. Until next time, watch all the other videos if you haven't already, because you need to be informed. And if you want to keep following, be up to date. Leave any comments or questions. Leave any questions or comments in the comments below. And yeah, I'll see you guys in the next one. Until then,